we will not get the next section finished today. So I'm just going to move that, not the one we're on right now, we will get that finished, but the one that's coming after that, we'll just get started on that. And we'll just push that to the next week again. So that's not a biggie. But anything that you can do from the next section, you know, whatever we manage to get covered at least, I'd do it just to reduce your workload, you know, for next week. So I'll move the due date sometime later today. Okay. Oh, have I got a comment I should be looking at? No. Okay. We've been doing these power series. I want to tell you a little piece of information that you sometimes are going to have to deal with, and that is that power series can be written in a number of different ways. And we're going to tell you a little bit about the style point rule for power series. Style points are just my phrase for the standard way that we would like things to be written in power series. This rule is not like carved in stone. So you will find textbooks that don't do it. And one of the reasons I'm pushing it is I'm working on the assumption that WebAssign might be pernickety, so that you may have the right answer, but it might not be the answer in the form that it was wanting. So I'm going to show you the standard form that power series should be. Power series, if possible, because they're not always going to be possible, should be written as x to the power of n. If you can make it happen, you should write them as x to the power of n. Of course, we do power series and all sorts of things happen. It's not uncommon to get x to the n plus 1s, right? And it's not uncommon to get x to the n minus 2s. We can take power series and convert them to this standard form, right? The style point form, excuse me, relatively easily. So I'm going to tell you the rule. If you want to reduce this, in this case by 1, to x to the n, whatever you do to every n. So see how this is going to go from n plus 1, reducing it to n. Won't the n cubed also follow it and be called n minus 1 cubed? Does that make sense that this and this are equivalent, except for a change in center? When you do that, whenever you reduce this by 1, you increase this guy by 1. So you see this bottom guy's now going to start at 4. So that's basically the rule of the game. If you add 1 to the power, you take 1 away from the sigma. If you reduce the power by 1, you add 1 to the sigma. It's a kind of a balancing game, right? If this goes up, that comes down to compensate for it, right? And if this goes down, that goes up to compensate for it. So suppose I wanted to take this guy and rewrite it in a form that maybe would be considered slightly better. Would you agree that I would reduce this by 1 to get the x to the n, which we're after? What would the n plus 2 become now?
N plus 1.
Right, you reduce it by 1. And it started off as n equals 0 infinity. What will it now become? If you reduce this by 1, what happens to that guy?
N equals 1.
Right. Are you happy about that? Just that's what you do to make it work, right? If the powers go up by 2, right, the sigma goes down by 2, right? If the powers go down by 3, the sigma goes up by 3, right? Seesaws. Right, in this case here, I want to rewrite it as a power series, but I want x to the n. That's our goal. Whatever else is going to be what it is, but you want x to the n. Would you agree in this case you're going to add 2 to the power to get x to the n minus 2 to become x to the n? Are you happy with that? You're adding 2. Now that means you add 2 to this guy. So, and by adding 2, I mean adding 2 that way, right? Not n squared plus 2, but n add 2 all squared. You see there's a big difference between those two things. Now, if you add 2 to this fella, what do you do to this guy then?
Adding 2?
Say again, Tim?
Oh, no, I think you add 2.
You may have said that the right answer is just I didn't hear
Oh,
you the
it's
first
going
time.
to be reduced by
Right.
2.
Yeah. If you add 2 to the power, you reduce the sigma by 2, right? If you take 2 away from the power, you add 2 to the sigma, right? That's the balance. This guy's okay, so we'll just leave it alone. Are we all, that was a little side issue just because some of your answers, you may put that in and WebAssign says wrong. And you're thinking, but I did it all right. So you have to change it and write this in instead. Okay. Now, I'm not saying that's going to happen all the time, but it probably will happen sometimes. And, you know, 4 questions, it's great. And then in the 5th question, it decides to be awkward on you. And you know, you just get frustrated because you've done the right answer, just not in the style point look that they were after. We are finishing off the power series as a function stuff with some heavy duty questions, really. So these ones you might want, you know, once I've done it, I hope it clicks. But if it doesn't, you might have to look it over a couple of times and read it over a few times before you get to grips with what's happening. This is essentially the whole question, right? And that's fine, and I've got it here. But I'm going to start from the top. That way, it might help you as we go through it. So here's the question. It's the same question, basically, that they give you. You're being asked to find the power series. But it's to be for this function. So these are special cases. You will not be able to use our 1 over 1 minus x guy or 1 over 1 plus x guy, because this is not 1 minus x. This is 1 minus x squared, and there's a negative 1 on top, which isn't such a big deal. But would you agree that we can't do substitution? This is not the method that we're going to do. It's trickier than that. That's what makes these a challenge. We need to find the function. And I'll even tell you what it's going to be. It has to be a fraction, right? So we need to find a rational function that you either differentiate or integrate. Doesn't matter what, but you're going to have to find a rational function that if you differentiate it or integrate it, you get that guy. Has anybody got any ideas what function you would start with? That if you integrated it or if you differentiated it, you would get this guy. That's the problem.
Maybe, so I think this is going to end up being like if we differentiate this, it'll be a u sub. And so we could go through, I think it ended up being something like 1 over u squared.
Mm-hmm. I think I know where you're going.
I was thinking possibly natural log, unless I'm confused. Trying to look up the
that particular one. If you go through the entire process that I believe Tim was describing, can I tell you that you will end up with that guy? Now,
and that's f prime, right?
That is basically f prime. Now, let's just take this guy and check him out. I'm saying that this function, when you differentiate it, gives you this guy, right? So I'm trying to find a function that if I differentiate it, I get this guy. So when we call this guy that guy, we've got a differentiation hat on. And if you want to differentiate this guy, don't you multiply by the power, reduce the power by 1, and oh, wait a minute, don't you also have to multiply by -1? And so what do we end up with is, oops, 1 take away x to -2, and that is 1 over 1 minus x squared. Oh, I'm almost right, but I didn't quite get it perfect, did I? How will I fix it without too much extra work? If that doesn't work, how will I make it work?
Multiply by -1.
Right. Bingo. We have found that guy. Now, if I kind of describe what Tim was doing here. Tim integrated this guy. When he integrated this guy, you didn't get what I said. You would find out you'd get that guy, right? But don't worry about the plus C. That's the guy you're after. Can you see how hard these questions are? Because it's not obvious who the fraction that you're going to deal with, right? And so you just have to play about with, I'll try this and see if it works. I'll try that, see if it works. You see how this one, after a little bit of tweaking, I got it to work, right? So what do we now know? Well, what we have is a function, which I'm just going to call -1 over 1 minus x, right? And what do I know about that function? I know that when I differentiate it, I get the guy I'm looking for, right? So what we now do is you get the power series, right? The sigma power series. So this guy's actually not that difficult. Isn't that guy just sigma x to the n? You agree? Now, that's not the power series I'm looking for, right? But if I differentiate this, is it not the power series I'm looking for? So let's differentiate it. If you differentiate this guy, you get that fella. And if you differentiate this, you get n x to the n minus 1. Great. What happens when you differentiate a function? Do you start at 0 or does this change? We talked about this at the end of yesterday. When you differentiate a function, what happens to the beginning? Is it n equals 0 or does it become n equals 1?
1.
1. If you integrate, it stays put. See, if you integrate, don't you just add a plus c at the end? Now, this guy is correct, as ugly as he looks. I guess it looks a little bit nicer like that. Let's do a style point on him. Wouldn't it be nicer looking? You have an x to the n here for style points. Now, if you do that, aren't you adding 1 to this guy? So add 1 to this guy. And what happens to this fella if you add 1 to the power? What happens to the start number? Moving my hands like a robot here.
Does it go down to 0?
It does. And there is how to find the power series of a weird fraction. I think it's living up to what I said. Very awkward, right? you won't have to think about each line and say, what the heck did they do and why did they do it, kind of thing. But eventually it will kick in. I think Molly's talking to a Texan. Are they saying you all?
No, she's not.
Why not? Oh, probably
Because
because
she's
she's
not from
not from
Texas.
Texas. Okay. Well. Okay. Here is a version of our second question, question 6. I'm going to keep this one here because it's got a lot going on in it. We're going to find the power series for a log function. And it's got the same problem. You need to figure out what you would start with, right? What fraction function you need to start with. And now, since that's a log, I'm thinking you need to have a fraction. And this ends up being the fraction, I believe. You can check the signs on it, but I believe this is the fraction. That's going to get me that guy. Let's double check it. If you integrate this, won't you get -1, the log of this guy, times a -1? Has anybody got any ideas how I got from here to here? How I figured out that was the right guy? I want to find the power series of this, but how did I come up with this fraction?
You differentiated it?
Yeah. So, you know you're after a fraction, right? So I'm thinking if you differentiate a log, won't I get a fraction? So that's the fraction I need. So if you can figure out where this came from, your life's going to become a lot easier for the next stage. Once you've figured out who this guy is, you then find the power series of this guy. Now it's a bit messy, but here's the guy, right? Have you noticed that I've sucked out the 11? You know, we did that yesterday. Because you have to have a 1 here, don't you? That fella became this power series. That 1/11th came in next door and gave us this guy. So are you happy about the negative? I'm just leaving it there. I could have brought it inside. The x to the n, the 11 to the n, and then this 11 comes in, and that gets you an extra +1. So this here is what the power series of that fraction looks like. I think my mind was just keeping that negative outside just to get it out of the road. Now, if you integrate this guy, you add 1 to the power, and you divide by the new power, you get that. And if you do the style point thing on it, do you see how I'm reducing this by 1, reducing this by 1, and reducing this by 1? So it becomes this prettier guy. But when you integrate things, don't you end up with the +c? So that's where we are right now. The natural log of this guy is c, take away this power series, and I've done the power series from n equals 1 to infinity. Well, we still have one little extra issue you don't have with the other question. That +c, which is here, has to be a number. We have to figure out what its number is. And we get it typically by plugging x equals 0. When you plug x equals 0 here, you get log 11. When you plug x equals 0, aren't all these guys 0 to the power of 1, 0 squared, 0 cubed, but aren't they just a whole load of zeros added up, which gets you 0? So the log of 11 is what c is, and now we know everything. Here is the power series for the natural log of 11 take away x. It's the natural log of 11 take away that ugly guy. I'll keep this here for a few moments while you try and digest all the stuff. I guess the only good news is that there's only one example of these questions, so it's not something you get a lot of. Any questions about that? This question 6, that question we just did. Okay. Are now on to a new chapter, a new section from chapter 11, 11:10. And it is Maclaurin and Taylor series. And I think I'll be doing mostly today, I'll be doing an intro to this, telling you a little bit about it. Kind of fascinating. Maclaurin, Taylor, I believe, is Irish or English. It's not Scottish. But Maclaurin is Scottish. And Maclaurin went to my university, Glasgow University. So I'm kind of proud of that. He wasn't a student there, but he did teach there as a professor. And he has a very interesting background if you look into it. He would be what you would call today a child's protege. He went to university, I think, when he was 12, when nobody would go to university when they were 12. You know, you had to be, you know, in many cases, you had to be in your 20s before you even thought about going to university. And we're talking 1600s here, right? Way back in the day. And he went there and he became, he went like zoomed through university. He got his doctorate when he was, I think, 17. And he became a full professor at 19. So, I mean, these are once in a generation kind of people like Newton, right? Fascinating guy. He had the world record for a long time as the youngest full professor. Some of the things you can't get immediately, right? You could probably zoom through, you know, do 2 years at university in one, right? If you're really bright, you can cut down the number of years, but you have to spend 2 years doing your PhD. Don't matter what it is, that's part of the rule, right? 2 years at least. You can take 10 if you want, but you must take at least 2. And it takes you 2 years to become a full professor, right? You have to be tenured, you know, and it takes a couple of years for that time. So if you take off those 4, that guy graduated when he was 13. I know, it's amazing. There are a few child proteges in the world. His record got beat by an American woman who became a full professor in, would you believe it? It was either Taiwan or South Korea. I can't remember now. So she actually, good kudos to her. But he is a Scotsman, and any Scotsman in my book is good, right? So don't worry if that makes you feel a little disheartened that I'm already by that age and I haven't got a doctorate or a full professorship. Nobody else has either, so you're in the same boat as the rest of us. So what did he discover? Well, we've been doing power series. I'm just making one up. That power series has x to the n in it, right? Or x to the 2n, or x, anything that's that. We say that this is centered at x equals 0. Whenever you see a power series that only has x, could be x to the n plus 1, x squared, or whatever, they are also called Maclaurin series.
Is that n factorial on the bottom?
Yes. In this case, it is. It doesn't need a n factorial. I could have put n squared at the bottom and it'd still be a Maclaurin series, right? Just be a different one. If, however, you have a power series, and we haven't seen as many of these, but they do have, where it's not an x, but an x plus 1 or an x minus 3, we say that this is a power series and it's centered at x equals 3, not -3, but 3. And when it's written this way, it's called a Taylor series. In fact, isn't a Maclaurin series just a Taylor series centered at x equals 0? So it's not that they're two different kinds of series, aren't they just the same series? One is a special case of the other. I have no proof of this because I didn't look into it, but I'm pretty sure what happened is Maclaurin figured out how to create these very special power series, because he's the guy that we're going to use to find the power series for things like e to the x, for instance, or sine x or cosine x. And they're almost always centered at 0. So Maclaurin got the in first. And then Taylor came along and said, well, that's pretty cool. And he just generalized it. Well, what happens if you don't center at 0? What happens if you center at 1 or center at 2? And you might think, why would you even need to center somewhere else? Can you imagine trying to do a power series of 1 over x if you centered it at 0? Wouldn't you have some problems with 0? Right? Some functions don't behave well at certain places. So Taylor figured a way of avoiding that situation. So we are now going to use, today at least, we're just going to focus on Maclaurin. And what he discovered is a way to find the power series for every single function in the universe. It's sigma n equals 0 to infinity. Funny notation, I'll explain in a minute. F brackets 0. See this little bracket with an n inside it? That just means the nth derivative at 0. Right, so you find the first derivative at 0, the second derivative at 0, the 200th derivative at 0. X to the n over n factorial, where that guy means the nth derivative at 0. Isn't that a remarkably simple formula for every single function in the universe being turned into a power series? So let's show you how complicated it can be. Let's find the power series for e to the x. Now, to be able to get the power series for any function, what you need to do is you need to find a formula, obviously using n, for the nth derivative at 0. So you need to be good at recognizing formula, right? Creating them from scratch. Right, so let's start with f of x. There we go. The value of the function at 0 is e to the 0, which is 1. Great. And let's take its first derivative. Oh, it's e to the 0. And the first derivative of 0 is still 1. Would you agree that e to the x is a very nice function to differentiate? Now, don't overthink this one. What is the nth derivative at 0 going to be?
E to the n.
Nope.
1.
What is the value? 1. Agreed? You overthought it, made it harder than it was. Which means that this fella is n to the 0 to infinity, 1, which I won't bother writing down, x to the n over n factorial. we have just found the power series for e to the x. Are we good? Now, I'm going to try, I think I'll do Desmos. I can't prove this formula to you. It's far too advanced. To be honest, I can't remember it either. I'm sure when I was at university, they proved it to me, but I've forgotten. But I will prove it to you in a different way. I'm going to, eventually, when I hit the right buttons, I'm going to try and convince you that this power series is e to the x. Would you like, do you think it's going to be hard for me to convince you?
I'm already convinced.
Oh, I could sell you a bridge right now then. Okay, shrink this darn thing up. Boom, 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 boom. There, that should be it, I hope. Maybe I should put it over here. That's much better. Okay. Okay, here we go. Took me a while to get Desmos. I should have set it up. Where is it gone? Okay. I've lost Desmos. Here we go. I think it's here. Zoom is just being awkward. Sorry about all this waiting. Right, I think I got it. Are you looking at Desmos now, guys? Yeah, okay, good. Let me shrink it up a little bit. I need to see as much as I can. Okay, now I'm going to put in here y equals, I believe I can get away with e to the power of x. I can. So that looks good. Okay, that's a pretty decent picture. Now, oh, darn it in space. I should plan ahead better. I have an infinite polynomial here. Of course, I can't do infinite polynomials. So I'm going to write down when n is 0, you get x to the 0 over 0 factorial. Then you get x to the 1 over 1 factorial. Then you get x squared over 2 factorial. Then you get x cubed over 3 factorial, and so on forever, right? Okay, a couple of weird ones. X to the 0 is the number 1. That's not too weird. 0 factorial looks like it should be 0. Can you trust me that 0 factorial is 1? And it's 1 because I'm telling you it's 1. But if you want to prove it's 1, go look up a function called the gamma function, which is actually where factorials come from. So if you're interested in factorials, look up the gamma function.
Is that the one with the funny hangman?
Yeah. Go looking at him, right? So if you can just trust me on that, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. So my proof is going to be pretty basic. I am going to sketch this polynomial and show you that it's a reasonably close fit to that guy, right? Now, why is it not a perfect fit? Well, shouldn't I be doing an infinite number of other terms, right? So let me go back to Desmos because I have it set up, and we should be able to plug this guy in. God, that's hard to say. Okay. Let's just do y equals 1 plus x plus x squared over 2, which is just another way of saying a half x. X squared. But Desmos has been a real pain here as well. Let me up this picture a little bit. Right. Okay. The green guy is, God, that's a stupid way of writing a half, isn't it? There, I can now see what I'm doing. There. Would you agree that the quadratic is not that good a fit to the red curve? But that's only because I only used x squared. Right. Let's take that guy and add one more term. Well, the next term is 1/6. So how about 1/6 x cubed?
We can't see.
You can't see Desmos? Ah! What can you see now? Did you notice
We
I
see
never?
Desmos.
Yeah. Do you see the quadratics and all this stuff as well? Right. Did you notice I never swore there? Was that not impressive? I just growled. My wife thinks it's cute when I growl, by the way, because I don't swear much. I do swear occasionally, but not much. If I move this around a little bit, if you look carefully, the red guy is the guy we want. If I zoom in a little bit more, would you agree that they're beginning to fit much closer? Right, the blue one is at least. Now, if I take this guy and I add one more term, which in this case is 1/24th, x to the power of 4. Do you see the purple one is beginning to fit that curve? Can you see that the more terms I add, if I take these two guys out now, can you see the more terms I add, the better the fit is getting? In fact, isn't it a perfect match up here and it's not so good over there? But oh, let's zoom out. Would you agree it's a really good match on this side? It's okay up to about -1 on the other side, right? Round about -1, do you see it's beginning to drift a little? But on this side, it was much better. If I wrote down, which I'm not, 2,000 terms, can you imagine that both of them would be on top of each other for virtually as far as you could see? Well, you were already convinced, Tim, but are you even more convinced that the power series works? It is actually just e to the x. That is a fascinating concept. I don't know why he even thought of going that road. I mean, you try to get into some of these people's brains, it would hurt. Because if you think of what we think of as functions, right, what you're thinking of functions before I told you about this, then you think sine x was just sine x, right? E to the x was just e to the x. That was who it was. If you'd said, oh, it's a polynomial, you would have said, no, it's not. Polynomials go wobblies, right? That's what polynomials do, right? They don't go EXs, right? And they certainly don't do sine curves. But nonetheless, they are, in fact, polynomials. They're just infinite ones. And because they are power series, that's all this is, they have radius and intervals of convergence. And what that basically tells you is that the power series works, but it tends to only work in certain intervals. If you're really lucky, like e to the x, it works for every value of x. But for some, -1 to 1 is normally the interval of convergence. So as long as you only draw the picture between -1 and 1, you can pretty much guarantee a perfect fit. And it'll be pretty good for the rest, but not, bang on. I thought that was pretty cool. So since we're in finding pretty cool stuff, here's something else. E. E is a number, right? E is about 2.7128, right? It's like pi, it goes on forever. How did they find out what number E was? It's power series. Isn't E what you get when you plug 1 in here. So e to the power of 1 is n equals 0 infinity, 1 to the n over n factorial. That's basically n equals 0 infinity, 1 over n factorial, which basically gets you 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, what's a 6, sorry, 1 over 4 factorial, and then finally 1 over 5 factorial forever. If you kept doing that forever, right, this guy, he converges, and he converges to e. So let me try it out and see what we get. I got 1 plus 1 plus 0.5 plus a 6th plus a 24th plus that guy, which is 5 factorial, plus 1/120th. And the answer that I get is 2.71 and some 6s. Can you see it's getting there? Now, if you wanted a more accurate version, wouldn't you just do 2,000 of these terms added up? Well, you'd probably get a computer to do it, wouldn't you? That's where E came from. They found out what its value was by just essentially getting its power series and plugging in 1. Are we good? So who should we try for the next one? Let's suppose for our last one today that I try and find the power series for the natural log of 1 plus x. This one's going to be a stinker, right? We're going to do it again centered at 0. So if I find the value of this function at 0, the answer we get is a log of 1, which is 0, right? If you find the derivative, it's 1 over 1 plus x, and the first derivative at 0 ends up being 1. If you want to get its next derivative, you're going to have to trust me on this. You get negative 1 over 1 plus x squared, and its derivative ends up being negative 1. If you want to find the third derivative, it ends up being positive 1 times 2 over 1 plus x cubed, and its derivative at 0 ends up being positive 1 times 2, basically over 1 cubed. So I'll do some cutting corners here. Can you trust me that if you find the fourth derivative at 0, it ends up being 1 times 2 times 3 over 1, and that the fifth derivative at 0 ends up being 1 times 2 times 3 times 4. The problem in creating all Maclaurin series is to try and find a formula for the nth derivative. And I should, by the way, I should be putting plus, minus, plus, minus. This sequence of values, starting here and going all the way down, can you see anything that would tell me the nth derivative? Can you see a pattern? Okay. Do you recognize what 1 times 2 times 3 times 4 is also called?
4 factorial.
Okay. If I call this guy 4 factorial and this guy negative 3 factorial and this guy plus 2 factorial, and can you trust me, this is negative 1 factorial and this is plus 0 factorial. If I do that, does it help you see that there's a pattern going on? The fifth derivative has a 4 factorial in it. The fourth derivative has a 3 factorial in it. The third derivative has a 2 factorial. What's the nth derivative going to be?
n factorial.
Very close. 5 gets you 4. 4 gets you 3. N gets you what kind of factorial? Not n factorial, but
N minus
Minus
1.
one.
n minus 1. Now, what about this plus minus carry on, right? Well, don't you get plus minus be using -1 to the n or -1 to the n plus 1, right? So if I wanted the fifth answer to be positive, that's the guy that would make it positive. We now have the power series for the natural log of 1 plus x. It's n equals 0 to infinity. The nth derivative at 0, which is this guy, x to the n over n factorial. We can simplify this a little bit. Can n minus 1 factorial kill off most of the n factorial? But when you do the cancel, isn't there still going to be an n left at the end? So we are now looking, and I forgot my plus 1. We are now looking at this guy. Let's write them down. If you plug in 0, you get a positive guy, you get a 1. Am I doing 0? Am I killing 0? I'm going to start at 1. That's fine. I'm going to get positive. I'm going to get 1. I don't need that guy anyway, right? Because he is 0. So I just skip by him. And so it's going to be 1. Then it's going to take away a half. Then it's going to be add a third. Then it's going to be take away a fourth. And then it's going to be add a fifth. And then take away a sixth. Do you recognize that guy? Oh, I should be putting x's. X squared, x's, x cubed, x to the 4, x to the 5, there we go, x to the 6, there, got it now. Almost missed my x's. Do you recognize that guy? If you plug 1 in, which is where my brain was going, isn't that the alternating series for the harmonic? And if you plug 1 in here, isn't that answer 1 plus 1 is 2? So I can tell you right now that the log of 2 is what you get from that guy. Remember, I'm pretty sure I mentioned it, that the alternating series, this guy, ended up adding up to the log of 2. And I said, oh, I'll prove it to you one day. I've just proved it to you. I just found its power series and I can plug in a number. In fact, couldn't you plug in 2 and get a power series for the log of 3? You could plug in a half, get the power series for the log of 3 over 2. This is really powerful stuff. What this does is it allows us to see functions with a totally new pair of glasses on, a new viewpoint. Still amazing to me. Although I've known it for years, it's still fascinating that functions are just infinite polynomials.
Got a question regarding that
Yeah.
polynomial. If I'm not mistaken, that series is only conditionally convergent, right?
Correct.
You said that back when we were doing conditionally and absolutely convergent series, you said that the reason that we have to define some of them as conditionally convergent was because if you switch around the order, it might change the
Yeah.
value it converges to. Is that true
Correct.
for this one here?
Yeah. As long as you keep it in that order, the answer's log 2. If you start mucking about with that order, you can make it add up to all sorts of weird stuff. So as long as you continue to add the next term, which would be plus the 7th, then take the one next to it, and you do the calculations in that order, you're totally safe. But don't do any other shuffling of those terms, because technically you could get any answer you want if you played about with it. And we have overshot your time a little bit. So I know your time's valuable, so thank you for hanging in here. say hi and bye-bye. Oh no, don't say hi and bye-bye. Say your last name and bye-bye. Have a good weekend. I'll see you on Monday. Come on, Tim, is this not fascinating that every function in the world is a power series?
I do find it pretty interesting. I'm going to be honest with you. It's kind of cool. Makes my brain hurt.
It does. It's you're looking at reality in a weird way, mathematical reality, because it's very hard to think anything in terms of infinity, isn't it? How can you have an infinite number of things? It really, essentially what's happening is the theory is that it's approximating the function, right? It's never exactly equal to it, but its limit is equal to it as long as you stay within its radius of convergence.
Yeah, I
But
think
even
that's one of the bummer
even
parts
that-
is, we used to just put numbers into math problems and then get numbers. Now we get something more complicated than the original problem.
Right. But some really cool stuff has came out of this. In the olden days before calculators, if you wanted to know what the sine of 1 radian was, the way you would do it is you had the power series and you would calculate it for maybe the first 10 terms, and that would be good to like 3 decimal places, and you put it in a book, and someone else bought the book and they would look up the sine of 1 and they'd read off what the answer was, and that way they could do it. So in the days before calculators, power series were the only ways that we could really calculate, in many ways, the value of functions. Right, if I went and said to you, what's the sine of 1 radian? You've got no calculator. You're stuck, right? But if you know it's power series and you're good at mental arithmetic and you can do it by hand, couldn't you eventually get the sine of 1, at least to 3 decimal places?
It'll take me a week, but I'm sure we could.
Right. Well, that's why they had monks. This was true. Monks did this job. They were one of the few literate people out there, and they basically were given, they did all sorts of jobs like copy books as well before printing presses happened, right? But one of the jobs they were given was to just do calculations. And from what I read a book once that said how they did it. They got 3 different monks to do the same calculation. And then the 4th monk checked the calculations. And if all 3 answers were the same, they were comfortable that that one was correct. If it was a 2-1 split, they would recalculate it a 4th time to see if it was the 2 people that were wrong or the 1 person that was wrong. And that's how they kind of did quality control, because you couldn't just let one person do it. Suppose they screwed it up and then you used their number. Couldn't you then screw up your answer because you weren't writing down the right value for the sine of 1? So life was difficult back in the day. We got it easy, calculators.
Isn't a calculator just a book that already kind of knows the answer?
Yeah. And it's a book that's got 20 decimal places well, that's an exaggeration, 8 decimal places anyway, which is much more accurate than probably the book would have. I am so old, this is true. When I started school, we had a book called the 6-figure table book, and it was just exactly that. I didn't have a calculator when I was at school. I got a calculator, I think, when I was 14, and I thought it was amazing. And all my calculator could do was the basic, sine, cosine, square roots, nothing clever.
So my dad's probably roughly the same age as you. He didn't get his first calculator until college, and he still has it. It's a Hewlett Packard, and it does all of its math in what's called reverse Polish. So
I've heard of it, yeah.
say if you wanted to do 1 + 1, you say 1 enter 1 plus, and then it
Oh
back.
God,
The
no!
first number to the second number.
My calculator was better. You actually could type in 1 + 2, and it would do it that order.
His had replaceable like modules that would come out the back. You could have extra RAM or programming modules that would connect to like a little machine that you'd put stacks of like these look like index cards. He still has it. It's pretty fun.
Oh, well, he certainly sounds like he got the early version before the, you know, the one I got had a little, it wasn't even LED. As far as I could tell, it was little wires that lit up so you could see the numbers. And it was batteries, you know, little batteries in the back, so it was pretty easy to use. Anyway, unless there's questions, guys, I'm going to kick you off now and get on with getting ready for my next class.
I do have a question.
Yes, Christian.
Number 8,
Uh-huh.
the
Are we talking Power Series one?
power series.
Okay,
The
number
0.8.
8.
I don't know if it's different for everybody.
It is. Let me go in and find yours, Christian.
Okay.
And that way I'll be using the same one. What's your last name, Christian?
Cartagena.
Gotcha. That's a Hispanic in origin? I'm just nosy.
Yeah.
Um,
Both. I guess I'm half Puerto Rican, half French. I guess according to my dad.
you got some French in there.
Yep.
I like French food. Not so sure my wife does. Right, what question are we talking about? 9?
Number 8.
Oh, 8. Okay, so you're half right in 8. What's the problem there?
So I got the first part. I understand the first part. I
Uh-huh.
just cannot wrap my head around the second part.
Okay, the second part says use a power series to approximate the definite integral I to 6 decimal places. Okay, so you've got this ugly power series which you got correct. So I'm going to write that down first, and then we'll show you how you're going to do the next bit. The next bit is just basically number crunching, which means you grab your calculator and keep doing it until you get the answer to the accuracy you're looking at. But I'm pretty sure you won't need many terms. Okay, so let me, oh, you've already got it, right? That's the guy that you got in part A, agreed? Right. Now, you're being asked to find the integral from 0 to 0.2 of basically this function, right? Because that's what this function was equal to. So what I'm going to do is I'm going to integrate this function, right? Which is this fellow. Now, if you integrate this function, the answer you get is -1 to the n, right? What do? You add 1 to the power, and then you divide by the new power. Are you happy with that?
Yes.
Technically, you should have plus c in it, right? But I know what's going to happen. I'm going to do it from 0 to 0.5. So can we assume then that when you plug in 0, you get nothing, so that's the c disappears. So all I really need to do now is find out what this fella looks like when x is 0.2. And this is where the number crunching kicks in. I'm going to write down the first few terms here. If you plug in n equals 0, you get a positive number, and it's 0.2 to the power of 4 over 4. And then the next number is take away. 0.2, if you plug in 1, you get 9. And if you plug in 1 here, you get 9. Then you do it for the third 0, 1. You do it for 2 now. When you do it for 2, it's positive, and 2 gets you 14, right? 5 times 2, that is. So it's this guy to the power of 14 over 14. That's just the first 3 terms. I'm 99% sure that that answer is probably already good to 6 decimal places. So 0.2 to the power of 4 divided by 4. Take away 0.2 to the power of 9 divided by 9 plus 0.2 to the power of 14 divided by 14. And the answer I got is that guy.
Yeah.
Now, if you turn that guy into a decimal, you will get 0.0004000. I think there's one more zero. And to 6 decimal places, you'd stop there. And that's the right answer.
Right.
So we used the power series of this guy to find an integral. And how do we do it? We just integrate the power series.